Good morning, students. Yesterday we discussed some of the fundamental properties of eigenvalues and eigenfunctions of a separable kernel, and now the next property is the eigenvalues of a symmetric square integrable kernel form a finite or infinite sequence which is denoted by lambda n with no finite limit point. Means we have to prove that infinity is the only limit point of the sequence of the eigenvalues. So let us include every eigenvalue in the sequence lambda n, the number of times is equal to its multiplicity. Now in the fourth property we already discussed that summation n varies from 1 to infinity, lambda n inverse whole square is less than or equal to double integral kst mod square ds dt. Now if we take uk be the sequence of orthonormal eigenfunctions corresponding to different eigenvalues, then from this equation, because this quantity is finite, so therefore this sum of lambda and n inverse whole square, that will also be finite. So from here we get summation n varies from 1 to infinity, lambda n inverse whole square, that is finite. And because the sum is finite, and therefore this further implies that the limit of 1 upon lambda n is 0 as n approaches to infinity. So we can say that infinity is the only limit point of the sequence of the eigenvalues. So this proves that the eigenvalues of a symmetric square integrable kernel form the sequence lambda n with no finite limit point. Now the next property is the set of eigenvalues of second iterative kernel coincides with the set of the squares of the eigenvalues of the given kernel. So let us take lambda be the eigenvalue of the given kernel and phi be the corresponding eigenfunctions. Now by definition, because phi is the eigenfunction corresponding to eigenvalue, therefore symmetric integral equation will be satisfied. So therefore we get phi is equal to lambda k phi. Now from here we get phi minus lambda k phi is equal to 0. So we can write it as I minus lambda k into phi is equal to 0. Here this I is identity operator. Now operating both sides by the operator I plus lambda k, this equation will become I plus lambda k into I minus lambda k operated on phi is equal to 0. So from here we get I minus lambda square k square operated on phi is equal to 0. So we can say that lambda square is the eigenvalue of second iterative kernel. Now conversely, let us take lambda square is the eigenvalue of the second iterative kernel, and let us take phi be the corresponding eigenfunction. So by definition, symmetric integral equation will be satisfied. So we have I minus lambda square k square operated on phi, that will be 0. From here we get I plus lambda k into I minus lambda k operated on phi, that will be 0. Now we have two possibilities: either lambda is the eigenvalue of given kernel or lambda is not an eigenvalue of given kernel. So let us take the first case. If lambda is an eigenvalue of the given kernel kst, if lambda is the eigenvalue of given kernel, then we have I minus lambda k, that will be 0. So if this quantity will be 0, that will prove that lambda is an eigenvalue, that will prove that lambda is eigenvalue of the given kernel. So in that case we have nothing to prove, the result is proved trivially. So let us take the second case. If lambda is not an eigenvalue of given kernel, if lambda is not an eigenvalue of the given kernel, in that case I minus lambda k will be not equal to 0. Now in this case let us denote I plus lambda k into phi by the symbol psi. So substituting this notation in the equation 1, we get I minus lambda k operated on psi is equal to 0. Now because lambda is not an eigenvalue of the kernel k, therefore I minus lambda k is not equal to 0. So from here we get the function psi is equal to 0. Now the value of function psi, that is I plus lambda k operated on phi. So this will be 0. So from here we get phi is equal to minus lambda k phi. So by definition we can say that minus lambda is the eigenvalue and the corresponding eigenfunction is phi. And this completes the property number 6. Now the next property is property 7, which states that if lambda 1 is the smallest eigenvalue of the kernel k, then the reciprocal of modulus of this eigenvalue lambda 1 is equal to the maximum of mod of inner product of the function k phi with phi, where phi norm is 1. And this maximum value is obtained when this function phi, that is the eigenfunction of the symmetric square integrable kernel corresponding to the smallest eigenvalue. In order to prove this property, in general we know that if lambda is the eigenvalue and phi be the corresponding eigenfunction of a kernel k, in that case symmetric integral equation is satisfied. Means we can write lambda k phi is equal to phi. From here we can find the value of k phi, which is given by phi upon lambda. Now substituting the value of k phi in the inner product of k phi with phi. So if we consider inner product of k phi with phi, that is equal to phi upon lambda and its inner product with phi. Now 1 upon lambda, that is scalar, that can be taken outside. Inside we have inner product of phi with phi, that will be phi norm square. So we have obtained the equation phi norm square divided by lambda, phi norm square divided by lambda is equal to inner product of k phi with phi. So from here 1 upon lambda is equal to inner product of k phi with phi divided by phi norm square. Now here lambda is any eigenvalue, and if we take this lambda as the smallest eigenvalue, then that expression will become maximum. So we can say that the maximum value of this quantity inner product of k phi with phi divided by phi norm square, that is obtained when the function phi is the eigenfunction of symmetric square integrable kernel corresponding to the smallest eigenvalue. So thus if lambda 1 is the smallest eigenvalue, then the reciprocal of mod of this eigenvalue is given by the maximum of the inner product of k phi with phi upon phi norm square. Because we can write this expression equivalently in the another form. If we take phi norm is equal to 1, so that quantity will become 1. In that case this quantity can be written as 1 upon lambda 1 mod is equal to maximum of inner product of k phi with phi. Here the norm of phi, that is 1. So this completes the topic fundamental properties of eigenvalues and eigenfunctions for the symmetric kernels.